Hi everyone, this is Chen from PUC-Rio de Janeiro. So today I would like to share with you a recent paper on the issue of detecting the spread of the so-called valence band Wannier functions by means of a bunch of optical sum rules that we propose in our paper. Basically, I would like to share with you how you can get from the experimental data of typical semiconductors or insulators, such as this dielectric function of silicon, how we can get from this kind of optical measurements of semiconductors to detect the spread of Wannier functions, the absolute scale of the spread, completely from the experimental data without any fitting parameter. Yeah, for instance, for silicon, we determine it to be 68.1 angstrom squared. Now, this issue of the spread of Wannier function is very intimately related to the notion of quantum metric. So let us first discuss what is the quantum metric. And also, this is a very hot topic at the moment. So consider you have a fully gapped semiconductor or insulator. And you have, suppose you have n minus number of valence band states. Now, because the electrons are fermions, so you should construct, if you wanted to construct one single state out of this all these valence band states, then you should combine all this block state wave function of all these valence band states in a fully anti-symmetric way, in such a way where this epsilon is the Levi-Civita tensor. Now, once you have this state, you can construct the so-called quantum metric by considering this valence band state at momentum k and a slightly different momentum k plus delta k. Now, if you consider the overlap of two such states and take a modulus of it and do an expansion, then you can prove very easily that the leading order expansion is quadratic in delta k, and the coefficient in front of it, this G mu nu, is what people call the quantum metric. And it has this very nice derivative form that you can see. Now, physically, what it means is that you can think of a quantum state as a unit vector in the Hilbert space, right? Spanned by some basis vectors that defines your Hilbert space. As you change from k to k plus delta k, your unit vector is going to rotate in Hilbert space. So basically, you are expanding the dot product of these two unit vectors in series of delta k, and it's like a cosine of the angle between these two unit vectors, right? So and the coefficient is naturally what you call the quantum metric. Now, this quantum metric is interesting, particularly if you consider the momentum integration of this quantum metric over the entire Brillouin zone. Now, because the quantum metric kind of measures the distance between k and delta k, k plus delta k, right? So if you make an integration over the entire Brillouin zone, then you're kind of calculating the average distance between neighboring block states in the entire Brillouin zone. And just for the convenience of discussion, we call this thing the fidelity number. And this has been discussed, raised a long time ago by the density functional theory people. Now, this number is particularly important because it is related to the Wannier functions. So what is a Wannier function? Well, you take a block state that defines your momentum space eigenstates. You Fourier transform it, then you can construct a Wannier state that is localized at some unit cell in real space. Yeah. And for instance, for graphene, you can take any orbitals. For instance, this is PZ orbital of the band structure of graphene. And you, if you construct a Wannier state by Fourier transforming all the eigenstates showing everywhere in this band, then you can construct a localized state. And as you know, the PZ orbital of graphene looks more like pointing out a plane, right? Or you can do it for other bands as well. Then you will be, depending on their orbital, the wave function will look different. Now, you can further construct what is the so-called spread of a Wannier function. Namely, you take the Wannier function centering it somewhere, let's say, suppose centering at the origin, And for each band, you have its own Wannier state, right? So this N is the band index, and counting the field band only. Then you calculate the expectation value of the Wannier state over the position operator square minus the expectation value of position and then square. Then this is kind of like a standard deviation, or so let's say the variance of the position of the Wannier functions or functions. Yeah. And this thing is known to contain two parts. One is the gauge invariant part, and the other one is the gauge dependent part. Now, a big issue in the density functional theory is how do you choose a smart gauge such that this whole spread will be as localized as possible, such that your effective theory building upon this Wannier functions will be more short range, then it will be more convenient to calculate numerically. So that is concerning this omega tilde here. However, in our paper, what we concern is the gauge invariant part, this omega I here, which because it is gauge invariant, then in principle, it should be experimentally detectable. And surprisingly, up to now, as far as we understand, no one has proposed a practical experimental technique to detect this spread of Wannier function. Yeah. So roughly speaking, this spread will tell you how wide are these these Wannier functions. And roughly speaking, you can think of it as how wide is the atomic orbitals of this solid. Yeah. Okay. And then it has also already been proved long ago by Souza et al. In 2000 that it turns out that this gauge invariant part of the spread of Wannier function has this expression, and it is equivalent to exactly the trace of this fidelity number that I was telling you earlier here. So that's very nice because that means if you manage to detect this trace of fidelity number, then you can have the information about this gauge invariant part of the spread. Now, how do you detect this thing? Well, it turns out that it is recognized recently by many people that the optical conductivity is equivalent to what we call the quantum metric spectral function and then times the frequency. So the optical conductivity of some semiconductors, non-interacting semiconductors, has this expression. Now you can argue simply from the Fermi-Golden rule. Yeah, so it contains this optical transition matrix element times the Fermi function, and also the part that conserves the energy. So basically, what is happening in optical conductivity is you shine the light into the material, and then you excite the electron from the valence band to the conduction band. Now, because the energy has to be conserved, so the frequency of this light will have to be equal to the band gap as preserved here. And the transition matrix element tells you how strong is this optical absorption process. And it turns out that this transition matrix element is precisely the quantum metric that I was telling you earlier. And therefore, this whole optical conductivity is actually equal to the quantum metric and times this energy conservation part. So in other words, if you go ahead and take integration over the entire Boolean zone, then you get what we call the fidelity number spectral function. And if you also go ahead and integrate over frequency of this fidelity number spectral function, then you will kill this delta function, and then you are simply left with this quantum metric in the transition matrix element of any optical absorption. Yeah. So in short, all you need to do is that you take this some real space optical conductivity divided by frequency, because there's a frequency factor here. You divide it by frequency and then integrate it over frequency. Then you get the fidelity number, and then equivalently you got a spread. Yeah. Okay. Then you go ahead and check any solid state textbook. You see that for three-dimensional semiconductors or insulators, which quantity will be directly related to optical conductivity divided by frequency? It turns out that there's a very simple one, namely the complex dielectric function, which is given by 1 plus I times exactly what we need. Yeah, this optical conductivity divided by frequency. But because there's a factor of pi here, so what you actually want is the imaginary part of this dielectric function. Yeah, so in other words, you take the imaginary part of dielectric function, integrate over frequency, multiply by some correct units, then you got exactly the fidelity number. And moreover, if you just multiply this integration over the correct unit, which will be given by the volume of the unit cell of the semiconductor, and then divide by angstrom, and more, and then there's a conversion factor 1.75 times 10 to the minus 3, just coming from some conversion of the fundamental constants. Yeah. So one typical experimental data that I'm showing you, you can use this recipe to get exactly the spread of valence-band Wannier functions without any fitting parameter. For instance, as I say, the dielectric function of silicon that has been measured since 70s and also been measured up to very high precision already. Here I'm showing you the real and the imaginary parts of this dielectric function. The real part is completely unimportant for my argument, so let us just look at the imaginary part, which is this green line that I'm showing you here. So essentially what I want is this area underneath green line, because I want the dielectric function integrated over frequency, which is precisely this area. Yeah. And for the silicon, you can extract the area just from this raw data. And for bismuth telluride, you can also extract this data whose dielectric function has been measured long ago. And this is quite interesting because bismuth telluride is actually a topological insulator. And there's also some relation between the quantum metric and the topological order that has been discovered recently. Yeah. So using this raw experimental data, we can extract the spread for silicon, germanium, bismuth telluride in absolute scale completely without any fitting parameter. For instance, for silicon is 68, for germanium is about 83, and for bismuth telluride is about 407 in units of angstrom squared. And you also get the trace of this fidelity number in absolute scale given by these numbers. Now, these are the 3D semiconductors. What about 2D semiconductors? Now, there are many such materials that have been discovered, as I will give you some examples later. Now, it turns out that the absorption power of 2D materials is precisely given by optical conductivity, because you know that absorption power is precisely a current times the field, right? And so that is also the optical conductivity times field squared. Then the absorbance of the material, or in plain English, this is just the opacity of the material if it happens to fall in the visible light range. Yeah. So the absorbance is precisely absorption power divided by the incident power of the light, which turns out to be also 4 pi times alpha, which is the fine structure constant, times the frequency, and then times this fidelity number spectral function. So our proposal is simply that the spread of Wannier function is given by the absorbance divided by pi times fine structure constant and divided by frequency, and then integrated over frequency, and then multiplied by the area of the unit cell, then you got a spread. Yeah. So the first 2D material you would think of would be graphene, right? So it turns out that graphene has a very interesting property on the absorbance. Namely, the absorbance is roughly a constant, roughly this pi times alpha in the visible light range. So, so if you have a constant and divided by frequency, integrated over frequency, then you know that you diverge logarithmically, right? Which does not make sense. So it turns out that for graphene, it is very important that this very small spin orbit coupling, which of the order of 24 microelectron volt, has been worked out by our collaborator, Denis, Kochan, and collaborators, that this very small gap in the absorption spectrum is enough to give it a finite spread. Yeah, and so we work out this integration. So in other words, the reason that this divergence, logarithmic divergence, is removed is because you don't integrate from zero frequency anymore, but you integrate from this small band gap, which is roughly 24 microelectron volt. And using this formula, we get graphene to have the spread about 2.36 times the area of the unit cell of the graphene. Now, another interesting system that we wanted to address is the twisted bilayer graphene. Now, this system has attracted a lot of attention because of the superconductivity observed in this material. And so basically what you do is you put two layers of graphene and slightly twist them such that they are slightly misaligned with a very, very tiny angle. And people discover superconductivity out of it. Yeah. And there's a class of theories saying that the superconductivity comes from the formation of the so-called flat bands because of this twisting. And especially there's some quantum metric in the flat band that is causing the superconductivity, as proposed by these authors. Now, so that means detection of this quantum metric is a very important issue for this particular system. Now, to address this issue, we use the tight binding model recently proposed by Bennett et al. That addresses the that gives an effective band structure for a wide range of twisting angles. And then we calculate its optical properties, which is given by this slide over here. So here we're showing the band structure as reproduced from the Bennett et al. Method, and also the quantum metric calculated out of it, and also the fidelity number spectral function, which again, as I said, is kind of like the density of states of this quantum metric. Yeah. And then also the absorbance, which is simply the fidelity number spectral function times the frequency. Okay, so and what is particularly interesting as a function of different twisting angles. So these 5 columns are in different twisting angles. And what is particularly interesting is the region of the flat bands in this model, which occurs at a twisting angle about 0.99 degree. As you can see here, the bands are very, very flat here. Yeah. And we calculate the absorbance, and we found that you will have a small peak roughly at the small, tiny little band gap between these two flat bands. Now, as I say, if you divide this thing by a frequency, then you get a fidelity number spectral function, and then you integrate it over frequency and essentially the area underneath this peak, then you get a fidelity number. Yeah, and using this method that we propose, you will be able to experimentally measure what the fidelity number spectral function, which is effectively the quantum metric integrated over Brilliant zone, as a function of different twisting angles. Yeah. And then if this is quantum metric is really responsible for superconductivity, then you can see if this fidelity number is really enhanced, let's say in the region where superconductivity occurs. Yeah. So this is our concrete experimental proposal to address whether this quantum metric is really somewhat correlated to the occurrence of superconductivity. Notice, however, that this absorbance is at a very, very small frequency range, and you see that it's less than 1 millielectron volt. Now, this falls into the region of what they call the millimeter wave region. So it's not a visible light range. Yeah, so it's a very, very long wavelength absorbance measurement that we are encouraging the experimentalists to do. Now, another class of 2D materials that have attracted a lot of attention recently are the so-called transition metal dichalcogenide materials. Now, there are many of them. Yeah, so we take a few of them that have already been investigated by a simple tight binding model by Liu et al. In 2013. We calculate its absorbance as a function of wavelength, and we compare with this experimental data proposed by Li et al. Now you see that experimental data is a little bit strange because I literally cropped them and then enlarged them such that they are in absolutely the same scale as our theoretical calculation. And you can see that this experimental data between the solid colored lines really match pretty well. Yeah. So this means that this Liu et al. Paper not only captured the band structure correctly, but also the transition metal matrix element, which or equivalently quantum metric and all that, very precisely. Yeah. And from there, we can also figure out the spread of valence band Wannier functions for this several TMD materials, and they roughly fall in the range of 17 to 27 or so. Okay, however, there's a big issue comparing our theoretical calculation of TMD with a real experimental data of absorbance. So there are several discrepancies. First of all, at low energy, you see some peaks in the experimental data compared to our calculation. Now, this is very natural because these are simply the excitons that are forming in these materials. Yeah. And however, if you really wanted to extract the spread of Wannier functions, then you should exclude these excitons manually by some means. Let's say you do a interpolation or something like that. The reason is because the excitons, they are bosons, and also they are usually only occur in some regions, very small regions in the Brillouin zone. So it does not seem to make sense to talk about the Wannier functions about excitons. So you should exclude them. And secondly, you see that although at low frequency it matches pretty well, but starting at photon frequency about 4 to 4 electron volt or higher, you started to see a discrepancy between the theoretical calculation, which is this black line, and the experimental data, which is this blue line. Yeah, and this we also understand. This is because the Liu et al. Band structure, they only take into account this tungsten bands at low energy, given by this blue and red colors. However, at higher frequencies, this very thin red lines, they mainly come from the sulfur atoms. They will also start to absorb light, and they will also contribute to the spread of Wannier function. Yeah. So therefore, to completely capture this experimental data, you really need to some time binding model or first principle calculations that can capture all the bands up to extremely high, the entire energy range. Yeah. But nevertheless, from these theoretical calculation, we can already capture the spread of Wannier function of the tungsten of the transition metal atoms very well. Yeah. So to conclude, basically we're proposing several optical sum rules. For 3D, you can detect the spread of Wannier functions by the frequency integration of the imaginary part of the dielectric function and multiply it by some correct unit, you get a spread without any fitting parameter. And for 2D, the correspondence experimental technique is the absorbance divided by frequency and then integrated over frequency. And that way you can also figure out the spread. Yeah, and particularly for TMD materials, and for twisted bilayer graphene, you can also detect the formation of the flat bands and also the quantum metric in this material. And that's it. Thank you very much. And if you have any questions, please don't hesitate to contact us.